Hello and welcome to the session. In today's session, we will be discussing about optimal binary search tree. But first information we need to know about is what is a binary search tree. Then we would like to discuss about how do we recognize an optimal binary search tree. So what is first of all, binary search tree is. A binary search tree is a binary tree, first of all, with the property that key on the left side of the tree are smaller than the root. So if this is the root and it contains a value 40, all the keys onto the left of the tree, right? This is 30, this is 10, and this is 20. This is 20, this is 10, and this is 30. So all these three keys actually are smaller than 40. So this left subtree, all the keys in the left subtree are smaller than the root element in this particular case. Similarly, for this node 20, this left subtree is smaller. And anything onto the right subtree for this particular node, it is going to be bigger than this particular node value, right? So key greater than the roots are onto the right side. So all the keys so this is valid for all the nodes of this particular binary search tree, right? So what you can see over here, the key 60 and towards left of 60 is 50. So smaller value is towards the left of it, and bigger value, which is 70, is towards the right of it. And 50, 60 and 70 all are towards right of 40 because they are more than 40. And all smaller values, key values, are onto the left of this particular node, that is containing the key 40. So, but why are keys arranged in this particular order in binary search tree? Well, one of the main reasons for doing so is that it gives an average, right? It gives an advantage in searching for a particular key. For example, if you are looking forward to search a key value 30, what you know is that it is going to be, so first you compare it with key 40, it is not 40. It is less than 40, right? So now you know that you need to traverse the left subtree in order to find the value 30, right? So what you find that, okay, so 30 is not here, so you go to the left of it. What you find, the value now is 20. So the value you are searching for 30 is more than 20, so you will move traverse toward the 30 value, that is towards the right of this particular subtree. And then you find here at this particular node that the value 30 or the key value 30 is this particular node, and whatever operation you want to do with this particular node, you can go on to do. Now, another key value which we may search is, let's say we search for value 9 in this particular tree, right? So now when we look forward to 9 is less than 40, okay? So we move to the left subtree, we reach here 20, then we compare it with 10. Once again, 9 should be towards the left of it. Unfortunately, now there is no value in the left of this particular subtree. So then this particular result, search is going to result into a failure, okay? So this is how you will come to a failure, where you reach to a node where you do not have any further subtree to traverse. So at that point of time, you say that I cannot find this particular value in the tree. Now, interesting part about this particular tree is that the number of comparisons is the cost of the searching tree. So if I'm saying cost of searching in this particular tree, one comparison I'll be making here, another comparison I'll be making here, and the third comparison I'll be making at this point of time. And in the case of failure, one comparison here, another comparison here, and I make another comparison here, plus now there is no part of the subtree, so we might include that also as cost in the cost, because then you have to report for the failure. Okay, so this is the way you are going to, the number of comparisons are going to determine the cost of searching the tree. Okay, now the question is this particular tree optimal? Or what is the property of an optimal binary search tree? Well, optimal binary search tree is the one which minimizes your overall searches within the tree. What does it mean? You may be doing various searches in a binary tree. You may be, for example, the binary tree which we were discussing, you may be searching for 30, 20, 25, 40, 50, 60, any key within that particular tree. All right. So, many searches will be performed, and the probability of different items which you are searching within the key, within the node will be different. And many a times your search is going to result into failures. Right? So, all these searches which you perform on that particular binary tree, right? The tree should be such that it answers you minimum number of comparisons. So, that is the basic concept. Now, a very interesting fact is how many binary search trees are possible for n nodes. If you are looking forward to n nodes, okay, suppose my binary tree has just n nodes, then how many binary search trees are possible in that particular case? Well, this is given by a recurrence equation where we are saying 2n Cn divided by n plus 1. So these are the number of binary subtrees which are possible given n nodes. Let's take an example for understanding this. Suppose the number of nodes are 3. Then the possible number of trees happen to be 6C2, because over here we are referring to 2n. So this becomes 6C2 divided by 3 plus 1, and n is 3. So 633 becomes 20 by 4, and how many actually turns out to be 5. Right? Even for n equals to 3, you have 5 possible subtrees. So if think in terms of when you have 4, this particular number will increase drastically. Okay, 5, it will increase even more greater. So this particular 5 trees which we have shown over here, all these 5 trees which are possible, this is one where you have the property of binary search tree is not going to be violated by any of these trees. Remember that, right? So this particular subtree 30, 20, 10. The property, that is the node onto the left are smaller. Okay, that is being maintained. Now next is 30. Then we have here it should be 10. This should be 20. Right. So 30, 20, 10, and right of that is 20. Next is 20, on the left 10, and onto the right 30. Then we have 10, onto the right of 10 is 30, and onto the left of it is 20. Then you have 10, 20, and 30. So these are the 5 trees which you could actually predict that these 5 trees are possible. So that is the way. The problem is actually exploding. As the number of or n, the value of n increases, okay, as the value of n increases, this particular number, that is the number of possible trees, are going to grow. Now, how do we find out that which of these particular trees, based on the search probability, is optimal. Okay, so this is our problem, finding the optimal binary search tree, right? And what is the formal problem definition? So we need to create a binary search tree which has a minimal cost given a sequence of K set, this is a set K, which consists of K1 till Kn of n distinct keys in sorted order. So if I'm talking about just when n was 3, then it was 10, 20 and 30. So K1 was 10, K2 was 20 and K3 was 30. So that's it. Okay, so the K set, we are referring to the set of keys. Set of keys of the nodes, right? So these are the nodes, okay. Each key Ki has a probability Pi that a search will be for that key Ki. So for every, suppose we are looking for searching 10, 20 and 30 and we make 10 searches, right? And out of that, 3 each are for 3 are for K, 10, 3 are for let's say for key 2, and there is no search for let's say one for key 3, and 3 search results are for failures. Then what we get, the value that is 0.3, 0.3 and 0.1 becomes the probability. So that is the probability we are referring to. Okay, so probability of looking forward to that particular key. Okay, finding if the search is for a particular key. Okay, some searches may be for the values that are not in the key. Okay, so that are not in the K. These are what going to result into failure. Therefore, what we need to create for them are n plus 1 dummy keys. Now, why n plus 1? We have just n keys, right? We will just delay the discussion on it. When we come to the diagram, we will know about it. Okay, so we have one more key than the dummy keys than the normal keys, representing values that are not in K, where D0 represents all values less than K1, okay, and Dn represents all values greater than Kn. Okay, so Dn will be representing all values greater than this, and for I equals to 1 till n minus 1, the dummy key Di represents all values between Ki and Ki plus 1. For each dummy key, we have probability Qi that a search corresponds to Di. So this is the naming convention we are following, or naming convention which we will be using this in this particular algorithm. Now let us visualize it, because it is the statement. Now we must have a visual representation for it. So this is the like we have K1, K2, K3. Okay, this is K4, K5. Remember, K3 is less than K4, right? But bigger than K2, right? That is why K1, K2, K3, K4, K5. That is the sequence of Ks. In this, we have 6 dummy keys, right? Which happens to, so we have 5 keys, K1, K2, K3, K4, K5, whereas dummies are D0, which is the less than K1, then Dn, which is D5, is more than K5, and then D4 is less than K5 but more than K4. All right, that's why it is placed over here. It is on to the right of K4 but left of K5. So it is in between, that is more than K4 but less than K5. Similarly, D3. D3 is going to be less than K4 but more than K3. Okay. Similarly, this value D2 is going to be that is more than K2 but less than K3. And D1 is going to be between K1 and K2, and that is what we state. Okay, so this particular case, okay, this particular case, what you look at is 40, 20, forget about these two nodes, okay. 40, 20, 60, 50 and 70. Okay, so if these are my 5 Ks, then you can say K1 is my 20, K2 is 40, K3 is 50, K4 is 60 and K5 is 70. So now in this particular case, anything less than 20 basically falls under D0. All the keys under which are less than 20 falls under D0. It's anything between 20 and 40, because 30 is not exist. These two keys are not existing, we are assuming. Okay, anything between 20 and 40 will fall in D1. Anything which is slightly more than 40 but less than 50 will be K3. It is going to be D2, right? So anything between D3 is going to be anything which is D3 is going to be somewhere here, K3, anything which is more than 50 but less than 60, like that. Okay, so like that you are going to predict all these particular values. This is how our binary search tree will be framed. Okay, now once we have framed this particular binary search tree, or we have looked into the example, now let us look into some more details as far as probability is concerned. Like probability that a search is for a particular key. A probability for the search is for a dummy. That is Pi and Qi. And remember one thing, the sum of all probabilities have to be 1. So let's look into the probabilities for every search. Now note particular thing. Every search is either successful or it's going to be unsuccessful. Okay, and the probabilities of search for each key and dummy key is this particular table shows this particular thing where I represents the node, right? Now remember one thing, this node number are K1, K2, K3, K4 and K5, right? These are the 5 keys which we were referring to. And 0 represents D0, right? So for the dummy node D0, okay, so this is the failure probabilities. Qi are the failure probabilities. Pi are the success probabilities. So suppose we are able to locate the node 1, right? The probability of search to node 1 can be 0.15. This is 0.10 for node 2. For node 3 it is 0.05. And node 5 being the most popular, let's say, the probability is 0.2. So let's count the probability of these, the sum of all Pi's and sum of all Qi's. How much it is, you can verify it for yourself. These are going to be, this is 60 in the first row, 0.6, and in this row 0.4, right? So total this is 1. The probability is 1. But the example which we are going to consider, we will not give probabilities in points, just for the sake of that you can understand the computation. Otherwise, the sum of probabilities has to be 1 as a problem. Okay. Now what is the expected search tree cost? Okay, with this particular thing. Assume that the actual cost of the search equals the number of node examined. That is what we had been saying. Okay, it includes the dummy. Either you do for the key value or the dummy. So that is what we are assuming. And we are also assuming the depth of the root node is 0. That is what we are assuming, that the depth of root node is 0. So depth of node found by search in T3 plus 1. So that is what is the number of searches. So if you are looking for root node, okay, so how many searches you have made? 1. If you are looking for anything below that, if you are going to that is next depth, that is level 1, then the number of searches will be 1 plus 1, 2. If you are going to the second level, the number of searches will be 3, like that. Okay, so this is the search cost E, which we are assuming. The expected cost of searching in the tree is basically for all I equals to 1 to n, all the nodes, for all the nodes, the depth plus 1, right? That is how we have assumed. The root node depth is 0 and searches will be required plus 1 multiplied by probability of each of those nodes. Okay, so the level of that particular node, that is the depth of the node, plus 1, because these are the number of searches, multiply by probability of that particular node, plus the depth of the nodes which are basically dummy nodes, right? This is for the dummy nodes. These are for the key nodes, right? And over here also it is going to be plus 1, because the depth is going to be plus 1 multiplied by the probability of those nodes. So this is the formulae. And technically speaking, you can take one out of all these equations out of the sum and just keep this as a particular thing. But we will use this particular formulae to determine the expected search cost of binary search tree. Okay. Now, all these things should go along with an example. If we do not discuss things with example, then you might get confused. So let us look into the example of the tree, okay, where we have K1, K2, K3, K4 and K5, and the dummy nodes D0, D1, D2, D3, D4 and D5 as the dummy nodes. Now their levels, okay. So K2 is at level 0, right, or the depth 0. So that is what K2 is at depth 0. K1 and K4 at depth 1. So K1 and K4 are at depth 1. All right. Then D0, D1, K3 and K5. D0, D1 and K3 and K5 are at level or the depth 2. All right. And thereafter D2, D3, D4, 5. They all are at level 3. Right. So what is the cost or the probabilities are whatever probabilities we had shown. We have just put in these probabilities over here. So what is the overall contribution towards the cost for these particular nodes? Obviously 1 depth plus 1. So this becomes 1 plus 1, 2 multiplied by 0.15, we get 0.30. In this particular case 0 plus 1 is 1 multiplied by this we get 0.1. So 2 plus 1, 3, 0.15. 1 plus 1, 2, 0.1 is 0.2. Like that, you can see, okay. You can try it in 3. 3 plus 1 is 4. 4 into 0.05, 0.20. And in the last case, 3 plus 1 is 4. Once again, multiplied by 0.41, we get 0.40. And the overall cost of this particular tree, okay, the cost of this particular tree happens to be 2.8. Okay, so the search cost in this particular case of tree is quite substantial. Okay, although what you can see, it is quite a balanced tree. Okay. Now, can we have a different tree? And in fact, this is another possible tree where you can see that even the K3, the number of levels in this particular tree are slightly more than the previous tree. Okay, over here we have just the depth of this particular tree was just 3. In this particular case, it is 1, 2, 3, 4 and 5, right? So in this particular node, we have the depth 5, yet this particular tree is showing a search cost of 2.75. So now it becomes very, very important for you to know that in an optimal binary search tree, for a given set of probabilities, right, an optimal binary search tree is not necessarily a tree whose overall height is smallest. Okay, so now you cannot say that the smallest subtree is going to have the smallest height, right? So for a given set of probabilities, we wish to construct an optimal binary search tree whose optimal search cost is the smallest, but it may not be the tree which has the smallest height. Then how to find the optimal binary search tree for a given set of probabilities? So we have come to, once again we are revolving around the problem, right? So we have come to that particular problem and the solution seems to be very, very simple. Draw all possible tree and pick the tree with the minimum cost. And this is going to take a very, very long time because as n grows, the number of trees grows tremendously. right? So this approach is not at all efficient. We need to design an approach which is efficient and doable. Many techniques in this particular case can be tried, but then in this particular case, the technique which can be tried is dynamic programming. And dynamic programming wants some basic characteristics, right? So let us look into dynamic programming approach for optimal binary search tree. First of all, we no need to draw each binary search tree and calculate its cost. So if we use binary programming, this is the advantage we are going to get. It gives a better and easier and faster method for trying out all possible binary search trees. You are still trying all possible binary search trees, but dynamic programming reduces the number of computation which you really need to perform because it allows reusability. Okay, so pick up the best one without drawing every subtree. You won't be drawing it every subtree, but then you will be utilizing many of those things. Optimal substructure. So the binary programming wants an optimal substructure. And what is that optimal substructure? If an optimal binary search tree T has a subtree T dash containing key, let's say K1, Ki to Kj, and dummy key Di minus 1 to Dj. Remember, dummy keys are going to be one less only, okay? One more, right? Starting from Di minus 1, okay? So if your keys are from Ki to Kj, dummy keys are going to be Di minus 1 till Dj. Okay, then this subtree T dash must also be optimal. So this is what in dynamic programming you want. The sub problem should also be optimal. It is going to, the optimal subtree, this subtree is going to be optimal too, right? So with this, the property of as far as what we say in this, we will be able to compute the cost in that particular way. So now the recursive approach, if we want to define for dynamic programming, it's going to be input. What we will be inputting to it, sorted distinct key Ki till Kj. In fact, we might put K1 to Kn. For each possible, now what we are going to do? For each possible root Kr, for I less than, I mean the value of R is between I and J, you will make optimal subtree for Ki till R minus 1 and Kr plus 1 till Kj. So this particular keys Ki till Kj will be, one will be picked as root and the remaining will be remaining till R minus 1. Suppose R is picked up as a root, then I to R minus 1 becomes left subtree of it and R plus 1 to Kj becomes the right subtree of that particular node. So this is the recursive formulation as far as dynamic programming approach is concerned. Search the root that gives the best total tree. So we are basically looking for roots, okay, finding the best roots. And we pick our subproblem domain as finding an optimal binary search tree containing the keys Ki till Kj, where I is greater than equals to 1, J is less than N equals to N, and J is greater than equals to I minus 1. J cannot be less than I minus, less than this value. Okay, so let's look into implication of this particular formulation. So what is the mathematical formulation of this? Well, mathematical formulation is let Eij be expected cost of searching an optimal search tree. This is what we are assuming. And let Wij is increase in cost of subtree, sum of all probabilities in subtree when we move the tree one level down. Then what we compute, actually we are interested in computing the overall cost, right? Expected cost from node 1 till node n, and Wij, which is sum of all probabilities, Pi's and Qis, and the value of Eij is going to be Qi minus 1 if j equals to I minus 1. What does it mean? we are referring to that the tree contains just the dummy key, D0. Alright, so if the tree contains D0, right, D0 is represented by what kind of value? I equals to 1, that is the key value 1, comma 0, right? So E1 comma 0 represents just the cost of D0. So that is why you are, because of these dummy values, you can go 1, J value can go 1 less than that. Okay, otherwise if J is more than this, okay, then EIJ is minimum of, that is the formulation we had was, the WIJ is basically the cost because we are making another level in the subtree, and this is the cost from I to R minus 1, that is the left subtree cost, and the right, minimum left subtree cost, minimum right subtree cost, and cost because you are putting all the nodes, you are creating actually the tree from the nodes of all the nodes available to you. So this is the mathematical formulation, slightly difficult to understand, but we will be, as we go into the algorithm and its description, you will find that this particular things are going to be easier as we go along. Now computing the optimal cost. So how we are going to compute the optimal cost? We will be writing an algorithm, and in that particular algorithm we will be storing EIJ, the cost value, in a table where we will be storing the value, the I index will be I till n plus 1 and J index will be from 0 to n, and the first index need to run to n plus 1 rather than just n, because to have a subtree containing only the dummy key dn, okay, we need to compute and store E n plus 1 comma n when you are referring to dummy key dn. This is going to be the cost, okay, the expected cost. And the second index need to start from 0 because to have a subtree containing only the dummy key D0, we need to compute this and store E10. This is exactly what I was referring to earlier. We use only the entries EIJ for which J is greater than I minus 1. Okay, J has to be greater than I minus 1. Okay, and we move forward. And another array we will be using, second array to store root I comma j for recording the root of the subtree containing keys ki till kj. In fact, if you remember what we did, we picked up one key as the root and left subtree and the right subtree. So we need that particular thing. The root is going to store the value of that. Then one additional table is needed, for efficiency. Okay, so compute the value of Wij, and store these values in the table W1 till n plus 1, 0 dot dot n. This is just related to E. And one thing which you know already is Wi minus 1 equals to Qi minus 1 for all the value of, it's a recursive formulation. Okay, for I less than, I is where n plus 1 is greater than I is less than 1. So this is what you are going to have. Note this particular part, W, the cost of the tree, where you are having the dummy nodes only. Okay, so that is what we are referring to. And for j greater than I, when j is greater than equals to I, then Wij has a recursive formulation. That is, Wij is computed with the help of Wij minus 1 plus add the jth node, that is jth key value, the probability of the jth key and probability of jth dummy. Okay, so that is how you are going to recursively formulate this particular value set. So let us try to look into the algorithm now for computing these values. Well, first thing first, now in this particular case, what we have done, okay, this is our algorithm, BST optimal, P, Q and N. P is the probability of keys, Q is the set of probabilities of dummies, and n are the number of nodes. We are assuming this particular example. We have taken keys as 10, 20, 30 and 40. PI values are taken 3, 3, 1, 1, 2, 3, 1, 1, 1. Unfortunately, they are not not summing up to 1. They are summing up to 16. But this is just for demonstration. Ultimately, in the last step, you can divide the whole value by 16. Actually, the probability of all these probabilities are 3 by 16, 3 by 16, 1 by 16, 1 by 16, and this is 2 by 16, 3 by 16, and so on and so forth. So if you divide every value with 16, okay, you will get the probability. But we didn't want to complicate the computation. That's why we have not divided that by 16. And you can visualize this particular simplicity in computation. The second thing available is that we have it's slightly shifted keys, but 0 belongs to this particular index, 1 belongs to this index, 2 belongs to this index, 3 belongs to this index, and 4 belongs to this index. Okay, so this is the way the keys are going to be dealing with. This table now, I is the value of I was varying from 1 to n plus 1, and the value of n is 4. 1, 2, we have 4 keys, right? So we have this I index varying from 1 to 5, and the j index was varying from 0 to n, right? So this is what you have. J is 0, 1, 2, 3 and 4. And the value of W represents Wij, that is 1, 0, okay, in this particular case. E represents the expected cost, and R is the root, right? So these value, this is the way this particular table will be organized. Right now, it is just been initialized. How it is initialized? With the help of this particular program, which is available over here. So we have 3 arrays, okay. We have already discussed about these 3 arrays and their indexes. W, E, W and the root. Root we will be storing which exactly contains the root. And initialization, what we are going to do? For I equals to 1 to n plus 1. So the value of I is going to vary from 1 to n plus 1. Now note this particular thing. Wi I minus 1 equals to Qi minus 1. That was the initial probability. Now initial probability in this particular case actually is 2 by 16, and we are just taking it as 2. Okay, just for the display sake. Otherwise probability is 2 by 16. We are representing it with 16 is assumed. Okay, divided by 16 is assumed in all these probabilities. So okay, so let's go for that. What way the values are going to change? W10, that is going 1 for I equals to 1, it is W10. What is that value? W10 is Q0. Q0 happens to be this particular value, okay, 2. So Q0 is 2. So this is what? The value of E as well as W, both will be 2. Then the next is going to be I equals to 2. Right, so 2 comma 1, W2 comma 1. Look into W2 comma 1. Okay, that's why this value is not marked. So 2, 1. What does it contain? 2, 1 contains Qi minus 1. I is 2 now. So Q1. Q1 is basically this value, right? Q1 is this particular value. So it is 3. All right, so W equals to 3, E equals to 3. Then comes Q2. Right, so W, then comes 3, W32, all right. So W32, now W32 is going to be Q2, right, I minus 1, I is 3. So Q2 happens to be this value, 1, right. So this is what you will see. Q3 is also 1, so that's what next value is going to be 1 and 1 over here. And for Q4 also, you will have, you can see I equals to n plus 1. So n plus 1 is 5, right? So 5, what is it's going to be W5 comma 4, E5 comma 4. So 5 comma 4 is this particular value. You can refer to this. And what is that value? Equals to Q, I is 5. So this is Q4, right? So Q4 is 1 in this particular case. So you can see the value 1 is getting. Technically, 2 by 16, 3 by 16, 1 by 16, 1 by 16, 1 by 16. All right? Okay. Now the next part. Okay. So now the algorithm moves to from initialization to final computation. Now what you do, now formulating the key, what you are going to do, you are going to try to figure out all the possible computations which are possible, right? And this is basically represented by the outermost loop L equals to 1 to n. So what you are going to do basically, you are going to start with first one key, okay? So that is being represented by L, okay? So L is representing, you will be just starting with one key, then 2, then 3, and finally n keys, all the keys. That means in our case, we'll be starting with one key, then 2 keys together, then 3 keys together, and then all the 4 keys. Now when the value of L is 1 to n, right, the value, what you will be doing? For I value, the value of I will vary when you are saying how many keys you are referring to together? 1. Then the value of I will vary from 1 to n minus L plus 1. Why? Because when you are referring to one key, you will be referring to 10, 20, 30 and 40 till 4 only, right? You don't have 5 keys, right? So key 1, key 2, key 3, key 4, okay? So you will be just computing for key 2. All key 2, 3, the keys 2, keys 1, key 2, key 3, key 4, 1 each, all right? And for that, the value of j, since we are referring to k, the value of j is going to vary according to I. How it changes, we will compute. We'll initialize some value. Let's try to figure out wij and eij, how they would be computed. Okay, that will give you good idea of how things are going to happen. So let's say the computation part of it. So just remember this particular formula a little bit, and we actually have reused them. So the value of L was 1. So what are the values for L equals to 1? What are the values of I? The value of I is going to be 1. N minus L, so it is 1. N minus 1 plus 1. So this is 1, N, right? So 1 to N, it becomes for the value of L equals to 1, right? So this is what it is, 1 to N minus L plus 1. L equals to 1, so will be computing 1 to N only. And in our case, we have 1, 2, 3, 4 values only, right? So it is going to be 1, 2, 3 and 4 only. Now what are going to be the related values of j in this particular case? Well, the value of j is basically was given by the formulation I plus L minus 1. Now the value of I for I value 1, L is always 1, right? So this 1 minus 1 becomes, this is 0. So it is I. So the value of j is I. So when I is 1, j is 1. I is 2, j is 2. I is 3, j is 3 and like that. Okay. And what was the value of wi comma j? The wij, the recursive formulation was wij minus 1 plus pj plus qj. Now this is going to compute one by one, right? This is first w11 will be computed, then it will result in E111 will be computation. But we have shown just all w values over here, just for the sake for simplicity. And once again, you remember, these are all divided by 16. Okay. So W11 equals to W10 by this particular formula plus P1, because the value of J is 1, right? J is 1 plus Q1. And what is the value of, what was the value of W10? In the previous diagram, you can see this W10 is 2, right? So that 2 value is being utilized. P1 is 3, over here P1 is 3 and Q1 is 3, right? So this becomes 8. So W11 becomes 8. W22 likewise will be computed to be This was 3. In the previous diagram, you can remember, this is 2, 1, right? And rest all are 1, okay? So W21 was 3, W32 was 1, W43 is 1, okay? And this will be requiring J, P2, J equals to 2, so P2 plus Q2. So this is how you are going to get 7 here, okay? In this particular case, you will get 3, W33 and W44, you are going to get 3. So 8, 7, 3, 3, all divided by 16, which we have omitted in the display. Now, is there any other value to be computed? Well, the computation for EIJ is also going to be done along with W. And how this particular computation is going to go? I and J, the value of I and J for L equals to 1 is once again the same, right? 1, 2, 3, 4, 1, 2, 3, 4, as was the case in W. But there is another value R, okay? In this particular algorithm, you say W computation is straight, but it is going on one by one. W will be computed, and so this will be. But R will be there for I to J. So this value, and thereafter this particular computation has to take place. All right. So this is what is there. So value of R is from I to J. Since I and J both are 1, so R is 1. Both are 2, so R is 2. Just, okay, R is 3 and 4, like that. Okay, and how this EIJ is going to be computed? With the help of this formula, which we had made in the mathematical formulation or recursive formulation. Okay, so it is I is 1, in the case I1, E11 equals to E1, R minus 1 becomes 0. The value of R is, in this particular case, the value of R is same as J, right? So E10, R is 0, R is 1, sorry. So this is E1 minus 1, 0, plus R plus 1. R value of R is 1. So this becomes 2, right? So E2 comma 1 plus W11. Now W11 in the last just iteration before that we have computed to be 8. And what was the value of E10 and E21? Okay, the value of E10 and E21 in our graph is shown to be, we have computed 10 and 21, you can see, okay, 2 and 3, right? So those 2 and 3 are getting substituted here and you get a value 13. And the root of this particular case, there is only one R, so R can be the root. R is basically the root we are referring to, okay? It is basically dividing the nodes into two subtree, left subtree and right subtree. This is just one node, therefore there is no left subtree or no right subtree, just the dummy keys onto the left and the right subtree. And that is why you are getting total, that is, the cost is slightly more than that, right? So 13, 11, 5 and 5. This is how this particular cost can be computed. Now this is what is being represented in this. So we substitute all W this over here. Now you see we have computed 4 values and they are all appearing in this particular case. All right. So just substitute this value. We are just getting an upper triangular matrix in this particular case. Now the algorithm continues. How it is going to continue? It is going to continue for the value of L equals to 2 now. Okay. Now for value of L equals to 2, interesting thing is going to be, now you are referring to 2 keys together. So what would be the trees? 10, 20, right? One node, one tree can be formulated with just 10 and 20 keys. Another node, another tree can be formulated with 20 and 30 keys. Another tree can be formulated with 30 and 40, right? So just 3 nodes are possible now, right? So that is what is represented. I1 to 2, right? I1, 2. So this is one tree with along with dummies will also go, right? That is there. But this is how it represents. 2, 3, the case is going to be this particular node, okay? This particular subtree. And 3, 4 is going to be this particular subtree. Okay, so you have 3 subtrees now you are referring to. Earlier you were referring to only just key and its dummy. Okay. Now you have 3 subtree only. Okay. And accordingly, the value of I and j will be adjusted. The value of L equals to 2, it is going to be minus 2 plus 1. So n minus 1. So it can go up to 1, 2 and 3 only, right? And j is going to be I plus L minus 1. L is 2. So this is going to be, that is I plus 1, right? So this is, if I is 1, j becomes 2, right? So this is, now you are referring to subtrees of 2 nodes, all right? So this is what you can see. The value of Wij is still going to be following the same formula. However, now the value of what value you are computing? 1, 2. All right. And this 1, 2 is basically this particular value. All right. I1, J2. So you are computing this particular values. All right. So 1, 2 will require 1, 1, which you have already computed as 8. And P2 and Q2, which are over here, P2 and Q2, which are 3 and 1, like that you have computed all the values in this particular case. All right. Now the problem with the R is going to be slightly different, right? Because in R, the value 1, 2, okay, and then 2, 3. The value of R is basically, R varies from I to J. So it will be 1 as well as 2, okay, for this first case. For 2, 3 case, it can be 2 or 3. For third case, it will be 3 or 4. And we will be applying this particular formula. Remember this particular formula? The value of R equals to 1 and value of R equals to 2 for E12. And how the formula is going to do this particular thing over here, what you see, I, R minus 1. So 1, 0, 2, 2. Why? Because R is 1. So this becomes 2 and this is J. J is already 2. So this is how it becomes. Okay. R equals to 2. This value will become 1. Okay. Because R minus 2 minus 1 is 1. So E11. Alright. Plus 3, 2. Okay. So these are the subtree costs. Okay. If R is your root node, then E1, this 1, 1 becomes your one subtree and 3, 2 becomes the dummy key becomes the second subtree. So that's how this subtree is going to be recognized. And Wij is going to be the other cost. Okay. So these are the two possible subtree situation. That is, you choose node 1 as the root. Okay. Onto the left, then you have becomes a dummy. Okay. And onto the right, then you have the subtree 2. That is one possibility whose cost is going to be computed by this. Okay. Or the second is that you choose root as the 2. Then onto the left of it, you have 1 as the K1 as the K1 and dummy as the left subtree. And onto the side right is just the dummy. And the cost computation is accordingly adjusted as far as these matrices are concerned. Okay. Now, the root is going to be the one which has the smaller value of the two. Now, what we find out of these R1 and R2, the minimum value is going to be is 25, right? So, the root of 1, 2, right? Because I is 1 and j is 2 becomes 1. Okay. Similarly, you find for 2, 3. The value for 2, 3. Okay. You will be able to find 17 and 30, 21 and root of this is going to be 2. For this, the first value is will be selected and the root will be becoming 3. And all these 3 values are substituted here. All right. Then we continue this algorithm for L equals to 3. Now the value will be just 1 and 2 and 3 and 4 for that. Okay, using the same iteration, you can work out. The value of W's now will be for 1, 3 as well as 4. So you are computing one tree is 10, 20 and 30. Another tree is 20, 30 and 40, and you are reusing all the time. Okay, reusing all content of the whatever you have developed is all the time you are just computing, and the value of wi becomes 14 and this particular value. And now in this particular case, the value of r, it can be 1, 2 as well as 3, any one of those, and 2, 4, 2, 3, 4. So you can see accordingly the indexes are going to be utilized, E11, E33 like that, and W11. Out of these three now, the smallest is this. So root of 1, 3 is going to be 2. Okay. And out of these three, where are the value of E24, the second subtree which you are referring to, the smallest is this 2, 4 equals to this one. So this becomes the, once again, this becomes your root. Okay. And these two values are substituted over here. And finally, we will compute it for L equals to 4, where I equals to 1 to 4 is going to be computed. And W value is going to be 16. Why? Because that is the sum of all the values. Actually, it should be 1. So 16 by 16 is 1. That's what you can witness. So this includes weight of all the nodes as well, all the keys as well as all the dummies. Okay. So that is sum of Pi and sum of Qi. 16. Why? Because we have not divided it by 16. Okay. And the computation for L equals to 4, we'll do it once again for 1, 2, 3, 4. You can substitute it in the equation, and you find that the minimum cost turns out to be 40, which divided by 16 is technically 2.5. And root happens to be 2 in this particular case. So this is my completely filled in table with W is 1, 16 by 16, and E is the cost is 14 by 16, which is going to be 2.5 in this particular case. Now, how do we finally compute the binary tree from this particular situation? Well, we start from here. What is the root? Root is key 2. So key 2 becomes, that is root 1, 4, right? 1, 4 is the final, okay? This where the value of W is 1. And the overall cost is 40 by 16, which is 2.5. So this is, root is 2, right? So my root is 2. 2 was key 20, right? So this is key 20, becomes the root. Now, when this is the case, what happens? When 2 is the key, then onto the left of it, we will have 1, that is key 1. Onto the right of it, we will have key 3 and key 4. Right? So therefore, we will be looking for root left. Onto the left of it is 1, 1, root of 1, 1. And the root of 1, 1 is 1. So this 20, 10. What about root of 3 and 4? So root of 3, right? 3 and 4. We look over here. Okay. So, and what is that? 3. Our root is 3. So this root becomes 3, which is node 30. Root 3 is node 30. Right? And root 4 obviously is singleton, so it is going to be R44, which is going to be R4. So this becomes my final tree as far as computation is concerned. So I'm able to establish this complete binary search tree with the help of this particular example. Mind, this 16 is 16 by 16 and this 40 is 40 by 16, just for the sake of simplicity. So let me try to summarize what we have covered in this entire example. For a given set of keys and probabilities of searches, a large number of binary trees can be made. Okay, we know that there are large numbers, so you know that. An optimal binary search tree can be found using dynamic programming. The solution requires maintaining tree arrays. There are 3 arrays, one for cost, which was E, one for keeping track of root of the subtree. If you want to compute the root of the subtree, that is the root one or the R1, and the third one is for sum of probabilities of the subtree. So the W1 is sum of all the probabilities. So try to see the mathematical formulation of this particular problem and look into the algorithm. Okay, we have provided the finer computations for you at each and every stage, and with this finer computation you will be able to figure out how this particular algorithm, dynamic programming algorithm, works for finding optimal binary tree. With this, I end this particular session. Thanks for being with me.